Hi folks, we're going to take a look at page 564, number 7. So they're asking us for the equation of the normal to this curve, which is likely a relation at the point 2, 3. So let's just recall what the normal to a curve is, and it is related to the tangent. Okay, so let's say I've got some curve, and if I want to find the tangent to the curve at some point, it's of course just this tangent line here. Okay, the normal is just the line that passes through the same point and is perpendicular to this one here. Okay, so this would be the normal line. Still passing through the same point and perpendicular to the tangent line. Now, you might be wondering, why might I be interested in the normal line? Well, one example would be if this represents the shape of a mirror. We know that we need the normal line to help determine how light reflects around about that point. All right, so let's take a look at solving this problem. So what we're looking for is the slope of this normal line, which is just going to be perpendicular to the slope of the tangent. So let me start by finding the slope of the tangent. Now, even if I wanted to, I couldn't isolate for y, so I do have to use implicit differentiation. All right, so we're going to start by taking the derivative of both sides of the equation. All right, and I would like you to always show this step here just to make it clear that you know how we start this. All right, so the left-hand side, well, obviously we have an addition subtraction. We're going to split these up. So derivative of x cubed, that's the easy one. It's just 3x squared plus, now remember to take the derivative of y cubed, we have to use the chain rule. So first we take the derivative of the outside function, which is y cubed, which gives us 3y squared as a derivative. And then we have to take the derivative of this inside function, which is just y with respect to x. Okay, and we leave it as is because this is in fact what we're looking for, the derivative of y with respect to x. Okay, minus, now here minus 3, might as well, 3 is just a constant, so now I have to take the derivative of xy, but because I've got a product, I need to use the product rule. Okay, so derivative of x is 1 times y plus x times the derivative of y, okay, dy dx. Now, notice here, I'm using Leibniz notation just because I want to be very clear what I'm taking the derivative with respect to. In the next step, I'm going to use y prime just to make it a little easier. All right, so here, derivative 17, that's just a constant, so that's 0. Okay, so the trick here now is to group together all terms that have the derivative of y with respect to x and bring all other terms to the other side of the equation. So first thing I'm going to do is I'm going to just simplify the left-hand side. So I've got 3x squared plus 3y squared y prime minus 3y minus 3x y prime. Okay, so I'm going to group together these two terms, and I'm going to factor out the common factor of y prime. So we got y prime, and then here we're left with a 3y squared, and here we're left with a minus 3x. All right, and then I'll bring to the other side the terms that don't have y prime. So I'll bring this one over first to make it positive, so that becomes positive 3y, and this is going to become minus 3x squared. And so finally, we can solve for y prime, and we have 3y minus 3x squared divided by this factor, 3y squared minus 3x. All right, so now that we have the derivative, what we were looking for, and we notice that our derivative, as with most cases with implicit differentiation, contains both x's and y. So that's why we needed to have the full point here. So now I'm just going to input 2, 3 into this derivative here. So let's say we have 3 times 3 minus 3 times 2 squared all over 3 times 3 squared minus 3 times 2. Okay, so what do we have here? We have 9 minus, well, 3 times 4 is 12, so 9 minus 12 is negative 3. And then here we have 3 squared is 9, times 3 is 27, minus 6 is 21, so it looks like we have negative 1 over 7. Okay, now remember, excuse me, remember that this represents the slope of the tangent, whereas I'm looking for the slope of the normal. Okay, so of course the slope of the line that's perpendicular is just the negative reciprocal, so this is going to be plus 7. And now I can take this. Remember, the normal still passes through 2, 3. So let's stick this into y equals mx plus b. So 3 equals slope of 7 times 2 plus b. So b is equal to 3 minus 14, negative 11. So our final answer is y equals 7x minus 11. All right, so before, actually, let's recap first. Okay, so step number 1 was to understand what the normal was. So it's just line perpendicular to the tangent. So I'm going to follow the steps to finding the slope of the tangent line. Here I have a relation or function defined implicitly. So I used implicit differentiation, which works by just taking the derivative of both sides of the equation. And in the process of simplifying, the derivative I'm looking for, dy dx, sort of appears as part of that process. And then the trick is to isolate that dy dx until you have an equation for which you can find a particular derivative. Okay, and in this case here, I use that to eventually find the equation of a line. Okay, so just to show you what this looks like here, let's look at Desmos. So we got Desmos here. So this is the relation. So it's not a function. And so if I graph 7x minus 11, I get this line here. But just to really show that it is indeed the normal line, a lot easier if we draw the tangent here. And it certainly does look as though these two lines are perpendicular to each other. And of course, they have to be, because if you look at the two slopes, we see that they're negative reciprocals of each other. Okay, that's it for this one.